it seems to me that we are currently recording the video. I hope, I finally hope. So, good afternoon to everyone, good morning, good evening to anyone listening to this lecture. My name is Anton Korban, and currently we're going to have a lecture in optical methods. So let me recall you that I've been talking about separation methods, followed by electromigration methods, and now the last lecture in my blog is dedicated to optical methods. So in this lecture, we will talk about various optical methods, and we will, of course, we will not cover all of them or even the majority of them, but we'll talk about some most important, most widely used methods that are employed in analytical chemistry and that differ greatly in their mechanism, in their principles. Well, let us first do a very short remembering. Let's recall some information about optical methods, why they're so wide, why there are so many methods, and why they're so not complicated but various, let's say. Yeah? It lies in the reason that electromagnetic radiation that interacts with our analyte may interact with its different parts. So it may be either nucleus or electrons or chemical bonds or the whole molecule. This will include some vibrational conditions, angles, bonds. So it's extremely complex, yeah, because your analyte may take energy from the radiation with its different parts, and different energy levels can be reached, and it means that you may follow almost everything. Yeah? And the second, not problem, the second way to variability is what do we actually measure. So mainly optical methods work the same. You mainly make the analyte to get energy from the radiation, but then the question is, what do you measure? You may measure either emission of the radiation, so when your analyte gives you energy back, or you may follow absorption, so when analyte consumes energy and you follow the changes in absorbed energy. The third variant is scattering and some other effects. So what are these effects? These exceptions, yeah? Where there is no energy transfer between compounds and radiation. Because, let me go back one stage. If we are talking about either absorption or emission, we are talking about energy, how to say this, energy catching, okay? Electromagnetic radiation may excite electrons, molecules, etc. So it means that there is some energy transfer. That's why exceptions, this third variant, is where there is no energy transfer between compounds and radiation. What do we call here? So, as I told you first, it is light scattering. When we just looking for how much, to which extent light is scattered. And few methods that we will not discuss today are nephelometry or turbidimetry. You have probably worked with this during some laboratory works, I guess. So usually use these methods to analyze solutions with really small particles. So it's actually white colored, but it is white colored because of huge amount of low size particles. So, and we measure this with nephelometry, how light can pass through the particles. So we may also speak about refraction of light, which is refractometry, interferometry. Let me recall you that refractometer detectors are employed coupled to some liquid chromatography or electromigration methods. Yeah? So actually we see some connections to previous lections. And finally, the third interaction of light with a compound is the rotation of the plane of polarized radiation, polarimetry. You have probably heard about sunglasses with polar filters. it is exactly the same. So polarization is changing the direction of light. Let me say this, that and some compounds may change the plane of some polarized radiation, and you may follow this. Okay. Now let us shortly speak about electromagnetic radiation. Let's recall some terms. Yeah, we were talking about this at the end of the previous lecture, but once again, let us recall some main terms and definitions. So, electromagnetic radiation is formed by photons of different energy, and electromagnetic radiation can be presented as a wave. Okay, and this wave is characterized by the following parameters. So the most important parameter is lambda, which is the wavelength. And so you can see that it is just the length between the same points of the wave. Yeah, because each wave has its maxima, minimas, and repeat and repeat and repeat. So wavelength, okay. And here you may also see the amplitude of electric and magnetic field, but actually you don't need this information in current course. Okay, let us focus mainly on wavelength. We'll need it greatly. So, as it is wavelength, we measure this in meters. Yeah? So the units of measure are meters. Yeah. Another property connected to wavelength is frequency. Yeah? Frequency means how many waves do you have per second. So how many times your wave will go up and down, so how many wavelengths are there in a second. That's why we have units of measure second power minus 1. So we use either this units of measure or hertz, which is this absolutely the same meaning, yes, second power minus 1. So how many waves are there in 1 second? The fact is that all photons are moving with the same speed, the speed of light. Yes, it is constant value that you should know. I think 3 multiplied by 10 power 8 meters per second. Okay, it is 2.999. So let me just take 3. So all photons are moving with the same speed of light. However, they have different wavelength and so different frequency. So the speed of photon is the same, but different photons with different energy they have different amount of waves at the same period of time, the same fixed period of time. So there are two main equations that you'll meet for photons and energy. The first one, which connects speed of light with frequency and wavelength. So you see that we just multiply frequency with the wavelength, and it means that the higher frequency we have, the smaller is the wavelength, and vice versa. If we have a really great wavelength, we have a low frequency. So if we'll try to draw this, let me check. So let us try to draw this just to understand. So is it here? Sorry. Yeah. So if we have a wave of a big wavelength, so lambda 1, and let's draw another wave as which quite smaller lambda. These two waves are characterized with different frequencies, of course. The frequency is, let us guess, at least 1, 2, 3, at least 3 times smaller. Okay. frequency of the second wave is at least 3 times bigger and 3 times smaller for the first wave. So, and as speed of light is a constant value, it means that here is the equation that wavelength of the first wave multiplied by its frequency is equal to wavelength of the second wave multiplied by its frequency. Okay. Oh, sorry, you probably don't see this. Let me move down. Yes, here it is. So lambda multiplied by nu is equal to the same value of to the same values of another wave. So let us continue. And the second very important equation is energy. We will talk about energy of the photon, and energy of the photon is directly connected to its frequency. Of course, you may use lambda as well. You may use wavelength, but you should just have used speed of light divided by frequency in this case. Yeah? So actually, you may use either frequency or wavelength divided by speed of light, or vice versa, sorry. Speed of light divided by lambda. Okay, what does this formula do for us? It shows us the energy of the photon, which is equal to frequency multiplied by Planck constant. So Planck constant is here, and actually it has really small value. It's just because we are talking about single photon. So yes, it is the energy of a single photon. We will use it because single photon can transfer energy as well, even if it is only one photon, and we will need this to work with different spectra. Okay, let us now focus on radiation, and probably you all have seen this picture for many times. It's a really good picture. I like it because, so here you may see radiation, which is depicted as wave, and you see as we move to the right, these waves become wider, 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 wider. So it means if we go towards to the right, the wavelength become bigger, but the frequency becomes smaller. So, and the higher frequency we have, the higher energy is. So it means that here is the most energetic, let us say roughly aggressive radiation, and on the right we can see really calm, low energetic radiation, yeah, which fully contributes to your experience, I think. So here you have some gamma rays, X-rays, ultraviolet, visible spectrum, of course, you should have known this. And it means that all of these types of radiation may interact with the compound, and we will see some of the examples today. But mainly we use ultraviolet, visible spectrum, and infrared radiation ranges. So let us have a short talk about quantification in optical methods. It's really important because optical methods are employed not only to make qualitative analysis, so not only to distinguish some specific molecules or analyze a compound or mixture, but to make quantification. And quantification in optical methods is performed by using Beer-Burger-Lambert law. You can also meet Beer-Lambert law or Beer's law name. So there were 3 scientists, but you may meet different names, 1, 2, or 3 of them. So what does this law state? It states that light absorption is directly proportional to the path length and the concentration of the solution. Really very simple equation, which states us that absorbance is the function of what? Of molar absorptivity, which means some empirical coefficient of our analyte. It means so just to which extent something absorbs light. Then path length, which is almost always constant because a glass vial which is used for the analysis is tabulated. Yes, it has the same, absolutely the same length. Of course, in rare cases you may use different vials, different cuvettes, but mainly you have this as a constant. And the third one, the third parameter is concentration. It means the bigger concentration you have, the higher concentration values are, the bigger the absorbance is. So really simple. And in practice, you usually have epsilon and L, you have this together as some empirical coefficient. And so you have A is equal to BC, for example. Yeah, so it's really easy. A very easy equation. Okay, now let's try to move something more difficult. And now let's try to speak about the UV visible spectrometry. Okay, let us first do the definition for those who may occasionally don't know. So ultraviolet, and visible. So by this abbreviation UV-Vis, we are talking about ultraviolet and visible radiation spectra. So if we go back, we are talking about ultraviolet and visible spectrum. So usually ultraviolet, we talk about near ultraviolet ranges, which are located somewhere here, but it's just extent to which we make our analysis. Okay, UV-Vis spectrometry is extremely popular method indeed. So you may see this method almost everywhere. It's extremely important because it's simple and it's really versatile. And you may do both quantity and qualitative analysis here, and it's quite good. So what's happening here? We measure the absorbance dependence on wavelength. Once again, if we're talking about, usually we're talking about UV or visible light, which has a wavelength of 200 to 800 nanometers. So what is actually happening here? In all optical methods, in absolutely all optical methods, you will meet such type of a diagram. Lots of them. There are lots of types of diagrams. But what's happening? You will have the only x of energy, and the higher the value is, the more the energy. And it means that after you treat a sample with a radiation, it moves to some higher excited states. And in this part of a picture, you see the electronic energy levels. So these are levels of electrons. Then to the right, you may see some vibrational energy levels, so which correspond to vibration of the bonds of the molecules. And to the right, you may see the rotational energy levels. There are lots of them. So there is extremely big amounts of different energy levels. Once again, if we are talking about some single electrons, vibrational modes of the molecule, or its rotational energy levels, there are lots of them. And the total energy of the system is just a sum of electrons, vibrations, rotations. And the biggest of them, let us say, I forgot the word, contribution is done by electrical energy. So that's why you can see in the picture that the difference between energy levels is so big. Then the difference between vibrational energy is around 100 smaller than those of electrons, and when we're talking about rotational energy levels, they are in their case 100 smaller than those of the vibrational energy levels. Yeah. Okay, and this results in a really broad spectra that we may see at the UV visible spectrometry. So these are not lines. Yeah? This is not a barcode, but it is a really broad spectrum because there are lots of different energy levels of everything. And that is the example of the UV spectrum. Yeah. So let us look at this graph. So what do we have here? The epsilon axis, we have absorption. So absorption, where do we absorb energy? And here on the x-axis, we have wavelength, yeah? Increase in wavelength, but so we increase wavelength but decrease frequency. It means that here we have photons with higher energy, here we have photons with smaller energy. And you see that the spectrum is aligned. Okay, we never have some 0 or 100% absorbance. We have some spectrum which will be unique for, or almost unique for, all the compounds that absorb light in this range. Here you can see the example of the absorption spectrum of the chlorophyll, and so you see that it absorbs light in the ultraviolet and in the red part of the spectrum. Actually, moving forward, let me tell you that that's the reason why chlorophyll is green, because you take red and violet color from the spectrum, and this one, and here is the range you see, and it means that you see here green and yellow colors together. Okay, what do we have here? Let us first look at the picture to the left. Once again, another ultraviolet visible light spectra. You see that some spectra has specific maxima, because we are mainly interested in maximal value, indeed, because we will use them later for the quantification, because maximas will lead us to sensitivity. You understand, if you select some wavelength here, of course it is possible, but you have no place to go down. Yeah, you have no space to go down, because if you will decrease the concentration, the peak height will go down under the same proportion, under the same ratio. So that's why we logically select lambdas with the biggest absorbance values. So, and here you may see also the example of aqua complex of titanium 3 ion. It's very nice picture because you also see colors here, of course invisible ultraviolet radiation for us, violet, and up to the red. And you see here also that the color of this complex is somehow violet. It is caused by the fact that you take near green and blue colors from the spectrum, leaving violet and red colors. So you may actually predict the UV spectrum according to the color of the compound. And here is just the small reminder, yeah, how everything works, because we'll talk about the same in atomic emission spectrometry. So you should understand and you should keep in mind, why do we see color of any compound? Yeah. So if compound absorbs some parts of the visible spectrum, so here on the left you may see that okay, let us say the rainbow of the visible light, green color is absorbed here. It is absorbed because its intensity is smaller, and that's why you see the white light without green color, which gives you purple. So and just for remembering that compounds that absorb UV radiation, so which absorb here, they are colorless. Compounds that are absorbing visible light, they are colored. Okay, and this is just a very nice table showing us what we will see regarding of which color is absorbed, which wavelength is absorbed. So qualitative analysis in UVVs is performed according to the how spectra looks like. Yeah? So you see similar molecules. Okay, they're not actually they're not very similar, but you see that we're just adding one carboxylic acid group, then we add another carbon, and so you see how spectra differs drastically. So by actually by measuring pure compounds, you may easily distinguish them just with the spectra. Yeah. You may work with the shape, spectrum shape, yeah, peak absorbance. So peak absorbance, it is the, once again, it is peak absorbance. It is one or few points of the highest absorption. Yeah? And you may also predict the existence of chromophores. We'll use this word later. Chromophores is the functional group which absorbs UV or visible radiation, because not every functional group absorbs light. These are usually aromatics and some conjugated p electronic system. These are really good examples of chromophores, and these functional groups makes these compounds visible in UVs. And quantification. So we use once again Beer's law, Booger-Lambert-Beer's law, which states us that the absorbance is directly proportional to concentration. So here you see two examples of spectra of the same compound, but of the different concentration. Yeah, let's follow this. Orange one is the highest concentrated solution, and we go down, down, down with the concentration. And as we go down, the same spectra, we see the same spectra. I mean, the shape of the spectra is the same, the absorbance maxima is the same, but the intensity differs. That's how we do quantification in UV-Vis spectrometry. Yes, and the same example here. And once again, different concentrations, we go up. Let's say a few words about derivatization. Let me recall you this wonderful word. Derivatization is procedure of changing the analyte in order to analyze it with a specific technique. When we were talking about gas chromatography, I was telling you that as not all compounds are volatile, we may do them volatile. For example, when we were analyzing fatty acids, we just transfer them to methyl esters to make them volatile. Yeah. When we're working with UVVs, it is sometimes necessary to make a compound visible for us, and so we add some chromophores. Yeah, we do this artificially. So we need some chemical reaction. So this at this time we need some knowledge of organic chemistry or inorganic chemistry. We need to add the chromophore in order to see this in ultraviolet or visible range. And so it is a very nice picture here. So you see that we're working with the same cation of chromine cation, and 3+, but how drastically changes its spectra regarding the ligands in its complex. So you can see that by changing ligand, you can easily shift the absorbance maxima to the left, to the right. Yeah? You may also sometimes use, so this is an example of using various ligands, but you may also introduce some chromophores. We were talking about this previous lecture when we were introducing big molecules to some peptides, and also we may perform some redox reactions because they may result in visualizing the molecule in UV-Vis range. Well, to sum up, let us discuss pros and cons of the UV-Vis methodology. So, first of all, it is really cheap to operate. It's important, of course, everywhere. And secondly, it is fast. Yeah? It is just a question of few seconds to make spectrum, so which is very beneficial for really fast and for fast analysis in practice. Also, I told you about destructive and non-destructive methods. If we are speaking about FID detector in GC, which is flame ionization detector, it of course destructs, leads to destruction of the sample because you simply burn it. But in UV visible spectrometry, you do not destruct the sample. It means that if you are limited with the sample, which of course is a very rare situation, but this may happen someday, it is non-destructive, which is positive. So also UVVs is quite sensitive, let me say, and selective as well, because different compounds absorb light at different wavelengths. It means that you have a library of unique spectra for each compound. And it is really good for quantification purposes. It means that it has good linearity range. It meets the requirements of Beer's law. It means that just absorbance is dependent on concentration, which is really good for us. When speaking about disadvantages of the method, you should understand that we are limited with the structural information. Actually, we gain no structural information at all, because you may just, if you do not have any library, so you cannot say anything about the structure of the compound. Also, there are some requirements to the sample. In UVVs, we prefer to work with clear liquids, so you need a solution. Sometimes you need to dissolve your analyte, clean it, filter, etc., 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 which brings you to some limitations. And the last disadvantage, it is the fact that we need some light absorbing groups. Yeah, it's important because without having this chromophores, you will not see the compound in this UVV's range, and it is bad, of course. And now let's talk about the instrumentation of UVVs. Actually, the instrumentation is really simple, and the instrument itself is really small. It's not very big, as for example GC, GCMS. But it may also be coupled to some separation instruments, as we have talked in our previous lectures. For example, it may be coupled to HPLC, and indeed, those of you who followed me to the HPLC practicum, HPLC lab, you have seen the HPLC actually coupled to UVVs. So that's how it looks like. Yeah, some examples of instruments. And this is the simple scheme of the instrument. Source of light, of course, you may not use a usual bulb. You usually use some deuterium lamps. However, just for demonstration, you need a source of light, then you'll need some lens. Then you may use or not use some monochromator. Monochromator means that you may leave only specific wavelength of light. It may be helpful in the UV range. We usually select only one wavelength of 230, I guess. You may leave only one wavelength or the whole spectrum, visible, ultraviolet. So you have this schematically at the prism. Cuvette with the sample, the same cuvette, and then the photo detector, which measures the intensity of light that passes through the sample. Okay, I guess that's clear. Let's move on. Let's move to the infrared spectrometry. And by the way, it is a really nice picture. I like it very much. Have a look at it carefully. So what do we have here? On this lower part, we may see different radiation levels. So you see wave number, it is a number of waves that is in 1 centimeter. You see the wavelength in meters. Yeah, so some parameters. So we have smaller waves here, and frequency. Of course, if we have smaller wavelength to the right, we have higher frequency to the right as well. And energy. Yeah, so you may compare energy of the photons. How does it changes? And of course, name of the radiation. And here on the top, you may see what's happening. Yeah, so it is interaction with nucleum, changing in electron distribution, electron states, these levels that we have seen before. And now we will be talking about infrared spectrometry. So we will follow different configuration, different angles and length of the bond. So now we need to exit the presentation because there is no animation in PDF. And let us speak about some vibration types in infrared spectrometry. So once again, infrared spectrometry follows changes in vibration types in molecule. So you give energy to the molecule. This energy is not enough to transfer electrons to higher energy levels, but it is enough to change vibration types. So, and there are some types in these vibrations. So first of all, let's talk about valence vibrations. Valence vibrations means that the atoms are moving in bonding directions. Yeah, and so it means that we change length of the bonds. That's why it is valence vibrations, because you move it here and there in the direction of bonds. And there are actually two different types, symmetrical or asymmetrical. Have a look here. I think it is really clear what is means symmetrical and asymmetrical. Have a look here. Okay, and in this case, we changed this valence vibration. So you see that difference is these vibrations results in different bonds length. That's why they are called valence vibration. The second type is bending vibrations. So, and atoms are moving in non-bonding directions, and which results in changes in angles. So bonds stay the same, but it rotates here and there, and it leads to different angles, to new angles. And here we have, oh my God, sorry. Here we have, once again, dividing into two different options. So first of them is planar or non-planar. It depends on if we have plane where the movement is performed or not. So first of all is scissoring. It really reminds scissors working. And the second one is rocking. So these are two types of vibrations which are called planar, because you may see one plane. Yeah, this is a limitation of such a distant learning. It's very hard for me to explain this, but you may just imagine the plane where all three atoms, these two white ones and two white atoms and black atom, are moving, are not leaving the plane. Yeah, and here as well. But also you may meet non-planar vibrations. These are wagging and twisting. Yeah? So, and you see that oppositely to planar vibrations, here there is no one plane of these atoms. They have lots of planes. Yeah, so they move in the 3D dimensions, yeah, not only in one, or not only in two, of course, I mean. So let us return back to the presentation. So You see that there are lots of molecule vibration types. And now let's see how does the infrared spectrum looks like. It looks like this. It usually contains lots of signals because many functional groups absorb different wavelengths, so which results in such a complex spectrum, let us say. And by measuring infrared spectrum, by interpreting it, you may predict existence of different functional groups, which is mainly some OH, CO, single bond or double bonding groups. And you may, sorry, you may predict functional groups that are in the molecule. Yeah? Here we have wave number, decreasing wave number, and different absorbance peaks. Sometimes, so infrared spectrum is usually depicted like this. As an axis, you have transmittance, which means how much light was passing through. If you have a really small value, like this peaks, it means that the light was absorbed and transmittance is low. Yeah, so actually you may move this spectrum from up to down. So just make a mirror here, and you will get a usual absorbance spectrum. But it's just usually presented in this, let's say, negative scale. Yeah, and so you see different wave numbers corresponding to specific bonds of the hexanoic acid. Which advantages and disadvantages are here? So infrared spectrometry is indeed very cheap to operate. Yeah? That's once again a great advantage. It is also fast and non-destructive, as well as ultraviolet visible spectrometry. And a very nice advantage of infrared spectrometer is that it is versatile. It means that you may measure solids, liquids, or gases. Yeah? You're actually very flexible with this state, and it's a great advantage, I think. It is excellent for identification of functional groups. Infrared spectrometry shows you the functional group's existence. And also, yes, I should have said this together with versatile advantage, but direct analysis. Yeah, you do not need sample preparation. So the sample preparation is really minimal when you're working with infrared spectrometry. So it's good. Yeah, we don't want to make some complex sample preparation procedures. Yeah. What about disadvantages? The disadvantages are the following. Of course, you get the information about functional groups. Okay, but you do not gain the information about the number of functional groups, and of course, you cannot judge the number of carbons. It is the limitation. Yeah. Oppositely to NMR or MS, that can give you much, let us say, not reliable, but it can give you more information about the structure. Of course, NMR and mass spectrometry, these techniques are just order of magnitude more expensive and more complex. Sometimes you will not get access to these techniques. Yeah, infrared is fast and cheap, but you cannot get any information about the whole structure. And also the limitation is that you will see the overlapping in complex mixtures. That's why if you do not have a separation technique in advance, you will see overlapping if you analyze a complex mixture of different compounds that absorb the same infrared radiation. Yeah? That's why infrared detector can be used in some LC separation techniques, electromigration techniques, as we were talking about in previous lectures. Yeah? Separation really helps to forget about this disadvantage. And sensitivity. Sensitivity in infrared spectrometry is, let us say, not so good. Okay, it's It's quite good in comparison with Raman spectrometry, which we'll be talking about now, but it's still not as low as in case of other techniques. And now let's talk about Raman spectroscopy. It's called under the Indian scientist Raman, and it's really something close to infrared spectrometry. It's really close because we are again talking about vibration modes of the molecule. But what is the difference? When we are talking about infrared spectrometry, we measure the absorbance of light. So we measure when we get the spectrum, so we just see at which wavelength do we have absorbance. However, in Raman spectroscopy, we follow the inelastic light scattering, or which is also called Raman scattering. What does it mean? In Raman spectroscopy, oppositely to infrared, where we have spectrum, we use only monochromatic light. Monochromatic light is done due to a laser. So laser, it is abbreviation, I cannot recall it now, but laser, it is abbreviation of monochromatic radiation. And after this radiation interacts with a molecule, it may scatter. It may scatter elastically, in elastic way, which is also called relay scattering, and it means that elastic means that there is actually no energy transfer between radiation and molecule, between photon and molecule, analyzed molecule. You see this green example where wavelength of the laser, wavelength of this introductive photon is the same. So it's just scattering without losing energy. That's important. But in Raman spectroscopy, we follow the Raman scattering. There are two types of this: Stokes Raman scattering and anti-Stokes Raman scattering. When photon transfers energy to the molecule, it means that it loses part of its energy. So logically, it means that after some energy was given to the molecule, photon loses its energy and wavelength becomes bigger. So this is the red case, Stokes Raman scattering. Wavelength of scattered light is bigger than the wavelength of the laser. Okay, so and part of the energy is here in the molecule. However, opposite situation may occur, which is called anti-Stokes Raman scattering. Things may happen so that molecule, if it is excited enough, will give part of its energy to the photon, incoming photon, and outcoming photon will have higher energy. So molecule will lose part of its energy and give it to the photon, and it means that this photon, blue photon, is characterized with higher energy and with a smaller wavelength. That's how you see anti-Stokes Raman scattering. Wavelength of the photon is smaller here. Okay, so in Raman spectroscopy we follow this blue one and red one. So we follow inelastic light scattering. It means that something happens, either energy addiction to the energy or emission. And as a light source, we use laser, but a laser of these ranges. So it is visible or near UV or near infrared. It means that both of them, near UV or near infrared, they are very close to the visible light range. And so you just remember that in Raman spectroscopy you're just working mainly with some visible light. And I have already told you about monochromatic light. and we register this shift in frequency. That's what we register actually, to which extent these photons changed their energy. And Raman spectrum looks, let us say, very close to infrared spectrum, because once again it is really close to infrared spectroscopy. They are really similar techniques, and the spectrum is again just a line with some absorbing maximas. And here you see the example of ethanol and methanol, quite similar molecules, but nevertheless there is some difference. Yeah, and here you may see some example of drugs, pharmaceutical molecules as well. And it is a very nice picture here, which contains Raman and infrared spectra together. So here on the top you may see infrared spectrum, and here on the down side you may see Raman spectrum. What is important to remember? What we can see in infrared, we usually cannot see in Raman, and vice versa. It's extremely important. So you should understand that Raman spectroscopy is usually used together with infrared, because this, how to say this, the nature of this vibration is so that actually infrared and Raman, they are showing us different functional groups. So I told you, and you have seen before, that infrared is really good for OH, CO, CO groups. Yeah, so you see a really nice absorbance peak. Yeah, but Raman spectroscopy is really sensitive for CC, CH, or C double bond C bonds. Yeah, and that's why really often, what you see very well in infrared, you do not see in Raman, and vice versa. So let's try to compare the spectra, and you may see that you may use these techniques together to get the best result of the analysis. Once again, our favorite slide with pros and cons. Absolutely the same as infrared, it is fast and non-destructive method, and the same as infrared spectrometry, it is versatile, so you again may work with solids, liquids and gases. But oppositely to infrared, it has no interaction with water, because I forgot to tell you that infrared spectrometry can be sensitive to water, because it contains once again this OH group, and OH group is really can be seen really nice at infrared spectrum. So if you have water with these groups, you may have spoiled spectrum. So you do not need you don't want water to be in the analyzed sample. However, Raman spectroscopy has no interaction with water, which is a great advantage in this case. And as for me, I think the most interesting advantage of Raman spectroscopy is that there is absolutely no sample preparation, and you may even measure the sample through the plastic or glass container. And I have seen this in practice once. It is used mainly in analysis, for example, of some liquids. For alcoholic products, for example, you may just take a small, how to say this, remote control instrument, which is really small. Yeah, it is just like slightly bigger than the mobile phone. And you just press the button close to the glass, and it shows you that it contains water, ethanol, and shows you the concentration of ethanol at really, how to say this, at really attractive concentrations, yeah, at really attractive accuracy of its concentration. So it's nice. It's extremely nice for fast analysis. Yeah, You may just you may imagine that you do not need any sample preparation. You do not even need to open the sample. Yeah, you may just measure it through the glass, through the plastic container. It's very good. And also, Raman spectroscopy, due to its high resolution, can be easily coupled to microscopes, and it is used with some microscopes to get images of some surfaces. But there are some disadvantages as well with this technique. It is characterized with, again, low sensitivity, which is even lower than for infrared. Yeah, so it is not possible to analyze some trace amounts of elements, trace amounts of compounds. Yeah. So we pay for this fast and non-destructive and measuring through the glass. Yeah, but it's okay for really express analysis. And also, if you have some fluorescent compounds, they interfere really well. It is undesirable. So, unfortunately, it is a disadvantage of this method. Well, and let's move on. Let's speak about the last part of this optical methods, really important part. It is elemental analysis with atomic absorption and atomic emission methods. So, what do we understand under the term elemental analysis? When we were talking about infrared, Raman spectroscopy, UV spectrometry, we were talking about analyzing of molecules mainly. Yeah? So we needed some chromophore groups, we needed some bonds that will vibrate, move, etc. But in the elemental analysis, our aim is to determine just specific element, which will be almost always this will be some metals, alkaline metals, D elements, D metals, and of course sometimes elements from this part of the periodic table. But for elemental analysis, molecules needed to be broken. Okay? So we need to break them and release a free atom. And we need to excite it. We need to excite our atom again with the radiation, which is again UV visible or near infrared light. What are these atomic spectra? The fact is that every atom that you may find in the periodical table has its own spectra. And here you may see the example of the whole light scale. So for those who don't know, this means angstrom, which is 10 power minus 10 meters. So it's just 10 times smaller than 1 nanometer. So it is 10 power minus 10. If you multiply it by 10, you have 400 nanometers or 4,000 angstrom. So just for those who may not understand this. So you see the full scale of the visible light, and here you can see 4 examples of different elements. And indeed, atomical spectra is a fingerprint. Yeah, it really is a very unique for every element. It's extremely interesting and very good. And atomic spectra are connected with electron levels. So atomic spectra are possible due to electron migration to some higher energetic levels. And of course, these levels will be different for various elements because of the different energy of orbitals and because of different nucleus charge, etc., etc., etc. So nucleus charge, different orbitals, different amount of electrons. So you see how greatly this spectra differs. And usually these spectra, atomic spectra, are presented as a barcode. So these are very thin lines, oppositely to UVVs, where we have seen a very broad line, a very broad spectrum without hardly determined maxima. Here we can see maximas really well, and that's a strong side of the atomic spectroscopy. And there are two types of atomic spectroscopy. The first one of them is atomic absorption spectroscopy, AAS. And here you may see the elements that can be analyzed with this methodology. So more than 70 elements, and which is great. As I told you, so we follow metals mainly with this technique. And so, as it is clear from the name, atomic absorption spectroscopy, we are following the atomic absorption. So we follow the light which is absorbed with an atom. Yeah. And so you see once again the whole spectrum, and these black lines represent what does atom absorb. And here you may see a very nice picture where you have some maxima absorbance for selected elements. And just have a look how small is the range. Yeah? So just remember that visible light range is 400, 800, or 380, 780. So it's quite a wide range. And here you are working with 0.15 nanometers, and you may see the let's say resolution of AAS. So you understand that if we change the scale to this, all these lines 2 to 8, okay, we cannot see this here because it is in ultraviolet range, but this will be a range, but this will be a very thin line, but still it is possible to distinguish different peaks here. So the resolution is great and it is very nice. And yes, I forgot to tell you that in AAS we're usually using either wide or narrow light range, and narrow light range is can be met more often. What does it mean, narrow light range? In UV, Vs, or infrared, you have a spectrum. You have a spectrum of radiation from to But in AAS, you often use some specific wavelength to determine specific elements. And very important topic here is hollow cathode lamp, which is used in AAS technique. What is it? So hollow cathode lamp is a common radiation source in atomic absorption spectroscopy. It is made of a desired element, and you have seen, have a look at elements that are analyzed. All of them are metals, yes, so we may do a cathode from them. So cathode is made of the desired element, anode is a tungsten wire usually, and the whole lamp is filled with the inert gas at low pressure. What's happening next? Then we apply voltage to this lamp, gas inside is ionized, and due to this ionization, cathode is ionized then, and this ionized gas interacts with cathode and release some excited atoms of the same element. And these elements release some specific wavelength. Just imagine that we have a sodium cathode lamp. Yeah, it means that our cathode will be made of sodium, and after applying voltage, it will release this specific wavelength of radiation. Why do we use these specific lamps? Why cannot we just use normal spectra? The reason lies, the answer lies in the fact that in order to neglect some negative effects that may happen when we're using the whole spectrum. If we use some specific lines for determination of the same element, yeah, we will get much better results in case of sensitivity and selectivity. So if your aim is to analyze sodium atoms to get sodium concentration, you take the sodium cathode lamp. It gives you some specific sodium radiation, sodium wavelength. You catch them, register them with a sample. Then you follow the absorbed light, because sodium in the sample will absorb light which is emitted with a sodium lamp. Yeah? So you need a specific lamp for a specific element. It sounds not very let's say suitable, yeah. So you think that we have so many elements, we need a cathode lamp for any element? Yes, indeed. But the great advantage is that using the same lamp will give you a really nice sensitivity. That's a great advantage. And of course, if you have 2 or 3 metals together, you will get multi-elemental lamps, but it will give you more lines. It will give you more lights at this radiation, and as a result, it may lead to some interferences. It may lead to some undesirable effects. So, of course, it depends on application. And yeah. So it was a question of light source, yeah. But now we need to talk about atomization. Our aim is to transfer sample to the gas state first, yeah, then to break all the molecules and all the bonds that can be here, and then release atoms. Atomic absorption spectroscopy as well as atomic emission spectroscopy works only with atoms. You need free atoms, free excited atoms. This will not work if you have any bonds here. So you need a really high temperature here. And so the first and the most common atomization technique is flame atomization. As it is clear from the name, here you have the picture. You use a flame to ionize the sample. In this type of atomization, we are using solution, just a liquid solvent, liquid solution of the sample, which is pumping again and again, which is pumped all the time through the system and then nebulized, yeah, for an aerosol. So it is somewhere below, under the flame. We have an aerosol in order to evaporate it easily. And then you burn it and everything happens. So you evaporate it, transfer to gas state, break all molecules, and release and excite atoms. And here you can see the part of the optical system. It moves, it goes through the flame, and then you register the absorbed light. What about pros and cons? Flame atomization is really simple and reproductive. These are really good advantages. Yeah. Once again, it is fast. You may perform analysis really fast, and it is characterized with a good linear range, which means that it is good for quantification purposes. Yeah. If you need to quantify some compound, flame atomization is a good selection. What about disadvantages? The sensitivity is not very low in comparison with the next atomization technique we will be talking. So the sensitivity is not really low. I'm sorry. And it's not very used for some volatile or highly melting elements. Yeah. So these are 2 disadvantages. The second more desired and more modern type of atomization is called electrothermal atomization, and it is based on using graphite tube atomizers. So it's just a tubing. You may see its photo here and its scheme here. The sample is introduced in this tube, and afterwards this tube is simply heating electrically. And you have light passing through, so optics here, and light going here. So what's the difference? What's the difference with with flame ionization? The difference is that in flame atomization, you constantly pump the sample through the tubing. Yeah, so you have a constant aerosol, and the lifetime of all the particles is really small. But here, when you evaporate this, when you heat the tube, all the sample stays in the tube for some time, which gives us more time to register some absorbance effects, which is good. Yeah? So there is no flame. Atomization is performed with this highly heated tube. And because of the fact that atoms stay longer in the chamber, in this tube, it leads to much higher sensitivity, indeed up to 1000 times increased sensitivity, which is excellent. The increase is very noticeable, just because of the fact that you measure the same analyte for a longer time. And also you need minimal sample volume, which is sometimes also a good advantage. When you are limited with a sample volume, you may use really small amount. And oppositely to flame atomization, where you use solution, which will be then nebulized. In case of electrothermal atomization, you may use gas, liquid, or solid analysis, which gives you some freedom, which neglects some sample preparation, and it's good. What's about disadvantages of this technique? It is longer. It takes longer time because you need to introduce the sample. Then you need to have some program temperature. It's done in some time, so it's not performed immediately. And afterwards, you need to clean this tube, which is done by heating it to really high temperatures. So it's longer than the flame atomization. Also, it is characterized with worse reproducibility. Maybe it is a problem of sampling, but the fact is that reproducibility here is usually lower, because when you are using solvents, solution is characterized with constant concentration. Yeah, you do not expect that at the beginning or at the end of your solution you will have different concentration. The concentration is the same at any point of the solution. Yeah. However, here the reproducibility can be poor, and the last disadvantage is that it is harder to optimize this electrothermal atomization in comparison with flame atomization. Here you need to optimize program. It is a disadvantage, but I think it can be act as an advantage as well. You can change the temperature. You can change the speed of heating. When you're working with flame, you have the same temperature almost all the time. Yes, you cannot change it in any way. However, here, when using electrothermal atomization, you may heat it drastically, so very fast or very slow. It's up to you. Which means that in case of some complex mixtures, you may somehow divide them, yeah, separate them with different temperature, and it is good when you have control under the temperature, but it's harder to optimize once again. Well, and now the last technique we'll be talking about today is atomic emission spectroscopy. It's really very close to atomic absorption spectroscopy, but it works on the different principle. So if we followed absorption in AAS, in AES we follow emission. So what atom emits. And usually it is performed once again with a flame, and probably you have seen this very popular picture of flame colored with different elements. And actually it is the most primitive usage of AES. When you bring some salts of different elements to the flame, they can color flame to different colors, and exactly the change in flame color is indicator of existence of some specific elements, which is used widely in pyrotechnical and fireworks. You probably all know this. So comparison of AAS and AES. So they are characterized with absolutely absolutely same lines. It's just because when we are talking about the same element, which is hydrogen here, it absorb and emit the same lines, the same wavelength of radiation. Why? Because the electron jumps here and there, and it jumps always the same stage. Yeah? And it means that the energy of the specific electron is the same, and the energy of the released photon or the energy of the catched photon is the same. That's why the spectra just looks like what do we absorb or what do we emit. And however, there is some difference between AAS and AES. The fact is, once again, here you have a picture of sodium absorbance spectrum, top one, and emission spectrum, bottom one. You see that all the lines of the absorption spectrum correspond to emission spectrum. However, emission spectrum contain more lines, and atomic emission spectrum can even contain more than 1,000 lines. As far as I know, it can be 5,500 lines, so too many of them for emission spectrum, yeah, which you will not see in atomic absorption. Yeah? And it means the reason of this lies in the fact that in atomic emission spectrum you also see some different some different vibrational modes as well. So you do not see only electrons, but also some other states of the atom, which leads to the fact that you see more lines in emission spectrum. And it usually works like this. So what if you would have a question, what is the difference between AIS and AAS? They're really very close techniques, but AAS is usually used for high selectivity analysis, and by using AES you may perform some multi-elemental analysis at the same time. Yeah, when we were talking about AIS, that's about using hollow cathode lamps, so lamps for specific elements, but AES will help you to analyze multiple elements at once, because you have lots of levels, lots of different lines, and it's much easier to analyze elements because you have more lines to follow for various elements. Okay, so that's everything I wanted to tell you so far. So let's just remember that Optical methods are based on interaction of light with matter, with electrons, or with nucleus, or with bonds, or with molecule itself. We may divide analysis of molecule or atomic analysis, elemental analysis, as we were talking about now. So, and we measured either absorbance or emission of light. And please don't forget that there is always also light scattering, as in, for example, in case of Raman spectroscopy. We can also follow light scattering or these effects like polarization and similar effects. So that's all for today. Thank you for listening and good luck.